Assalamu alaikum. This is lecture number 6, Physics 281. Today I will discuss homework number 3. The first problem, to find the general solution for the equation of undamped simple harmonic oscillator driven by a force of the form F0 sine omega t. The equation of motion is mx double dot plus kx equal F0 sine omega t. There is a missing term here in this equation, the damped term, which is 0 in this case. The equation, first divide by m, then we know that the second order differential equations has two solutions. The homogeneous solution, which is given by a cosine omega 0 t plus b sine omega 0 t. Omega 0 is square root of k over m. For the particular solution, since we have a sine omega t, we have to put the sign as exponential e to the power I omega t. So xp has the form, the imaginary part of some constant c times e to the power I omega t. Now we need x double dot p. This is x double dot, which is minus omega square c e to I omega t, and we need x, which is c e to I omega t. Then substituting in this equation of motion, we get this minus omega square plus omega square sub 0 c e to I omega t equal f0 over m times e to I omega t. So we get from this equation c equal minus f0 over m over omega square minus omega square c. Hence the particular solution is the imaginary part of c, which is this expression sine omega t. Now if you look at this expression, the amplitude is function of omega. We have to plot this as function of omega. At omega equal omega 0, this expression is divergent. If you approach a sub b from left, it shoots to infinity. From right, it goes to minus infinity. At omega equals 0, we get minus f0 over m over minus omega 0 square, which is f0 over m omega 0 square. The general solution is a cosine omega 0 t plus b sine omega 0 t minus f0 over m by omega 0 square sine omega 0 square. Now the second problem, we have a potential of the form v sine omega t and three components: inductor, capacitance, and resistance. The current is given by this expression I equal I0 sine omega t minus phi. The first question to find I0 and phi. The second is to show that this has maximum, the current has maximum at omega 0 equal 1 over square root L C. And the final question is to find I, the value of I and phi at the resonance frequency. To do so, we apply Kirchhoff's law. The potential V0 sine omega t equal to the potential across the inductor plus the potential across the capacitor plus a potential across the resistance. We get this equation. Now we know I, we need I dot di by dt, which is given by this expression, and we need a q. To find the q, we integrate I with respect to dt, we get minus I0 over omega cosine omega t minus phi. Now substitute for q and I dot, we get this expression. Now write cosine omega t minus phi as cosine plus sine, and sine omega t minus phi as sine cosine minus cosine. We get this equation. Now the coefficient of the cosine omega t gives this equation, and the coefficient of sine omega t gives the second equation. you can write this, the right hand side of this equation is plus 0 cosine omega t. Now from the first equation we can get phi, which is down phi is sine phi over phi, which is omega L minus 1 over omega c by r. Now to get the current I0, we have to square the first equation and the second equation and add them together. Doing so, we got this expression for equation number 1 square, and this is for the second equation. When you add them, the cross terms cancels, and now simplify, we get I0 equal V0 over square root R square of omega L minus 1 over omega C, the whole thing square. This has maximum at omega when this expression equals 0, that's omega L minus 1 over omega C equals 0, or omega square equal 1 over LC, or omega equal omega 0. Now, if this is maximum at omega 0, if you substitute omega 0 here, you get I0 equal V0 over L. And that's it today. Thank you. See you.